Hello and welcome to Weapons of Math Instruction. This is the third in my series of videos on uncommon integration techniques. Every Calculus 2 student learns how to integrate power series, and some even learn how to use power series to approximate integrals. But it's not part of the standard Calc 2 syllabus to use power series as a technique to find the exact value of an integral, and that's what I'll be discussing here. I have two examples that I want to show you using this technique, but the first example is kind of long, so I split my discussion into two videos. In this video, I'll be assuming that you saw my last video in this series, which was on Euler's identity as an integration technique. I'll post a link to that video in the description in case you need to refer back to it. So I'm going to illustrate this technique with this example right here, the integral from 0 to pi over 2 of the natural log of 2 cos x dx. Now, as I mentioned in the last video, I showed you Euler's identity, e to the ix equals cosine x plus I sine x. Now, if I replace x with negative x, I get e to the negative ix equals cosine x minus I sine x. And that's because the cosine function is even and the sine function is odd. Now, if I add these two together, I get e to the ix plus e to the negative ix on the left. And on the right, these two terms cancel out and I get 2 cosine x. And if I solve this for cosine x by dividing by 2, I get that the cosine of x equals e to the ix plus e to the negative ix over 2. And I'll be using this identity here to correct the integral at the top of the slide. So here I've plugged in the identity for the cosine of x and I've canceled out the 2's. And what I have here is the log of a sum. Now I'd like to write this as a log of a product so that I can use the property of logs that allows me to split up logs of products. So here I factored out e to the ix, leaving me with 1 plus e to the negative 2ix. And now I have the log of a product. So here, I've written the log of the product as the sum of the logs of the factors. And here, I split this single integral up into two integrals. And I'll call them I1 and I2, and I'll work them out separately. So here's I1, and this one's a piece of cake. The natural log of e to the ix is just ix. Now, I'd be remiss if I didn't bring up a technical point. In this integral, we're dealing with a complex logarithm. And in the complex domain, the logarithm is a multiple valued function, and so it doesn't have a unique inverse. For instance, the natural log of e to the I pi over 2 is indeed I pi over 2. But the natural log of e to the I 3 pi over 2 is negative I pi over 2, not I 3 pi over 2. But over this interval of integration, we're working with what's called the principal branch of the log function, and so everything that I'm doing with complex logs in this example is correct. Okay, that technical point aside, we'll use the power rule for integration to get ix squared over 2, evaluated between 0 and pi over 2, and if I evaluate that bracket, I get I pi squared over 8. Okay, on to I2. This one's going to take more work. And here's where the power series comes in. We're going to use the Maclaurin series for the natural log of 1 plus x to get a series representation of the integrand. So here's the Maclaurin series for ln of 1 plus x. And note the similar forms of the arguments of these two logs. This is 1 plus x, this is 1 plus a complex exponential. It's the similarity in those forms that is exactly the reason why I decided to use this technique. So plugging in e to the negative 2ix for x in this series gives me this series representation for the integrand. The sum from 1 to infinity of negative 1 to the n minus 1 of e to the negative 2ix to the nth power over n. So here I've substituted the series representation of the integrand into I2. And I want to focus on the integration, so I'll tidy this up a bit. So here I've done a few things. I've switched the order of summation and integration for one thing. And I brought outside the integral anything that doesn't depend on x. So negative 1 to the n minus 1 over n, that has nothing to do with my integral. And another thing that I've done is I've multiplied these exponents together to get an integrand of e to the negative 2inx. And this integral is easy. When you integrate e to the negative 2inx, you get negative 1 over 2in, and then e to the negative 2inx evaluated from 0 to pi over 2. Evaluating this bracket, I get e to the negative in pi minus 1. And I'll carry this to the top of the next slide. Okay, so here's where I left off with I2. And note, e to the negative in pi is cos n pi minus I sine n pi. That's Euler's identity. Now the sine of n pi is 0 for all n. And the cosine of n pi is 1 when n is even, and it's negative 1 when n is odd. So, this expression here just equals negative 1 to the n. So here I plugged in negative 1 to the n for e to the negative in pi, And I've done a few other things too. This factor of -1 right here, I combined it with this -1 to the n minus 1 to get -1 to the n. And I took this 1 over 2i and pulled it all the way outside the sum, and I brought the I to the numerator to get -i over 2. And I combined these two factors of n to get n squared. So this is a lot cleaner than the line before it. In this step, I took this -1 to the n and distributed it over these two terms. So -1 to the n times -1 to the n is just 1. And -1 to the n times 1 is, of course, -1 to the n. And note, this numerator right here, 1 minus -1 to the n. If n is even, this thing is 1. So we get 1 minus 1, which is 0. And if n is odd, this is -1. So you get 1 minus -1, which is 2. So every term with even n is 0, and we don't need to include them in our sum. So in this step, I replace 1 minus -1 to the n with a 2, because that's what this equals when n is odd. And also, I've changed the index of summation. And I changed the denominator of the sum n to 2k minus 1 squared. So I'm forcing this quantity in parentheses to be odd. And as one last little cleanup step, I just cancel these 2's. So here's my final value for I2. So let's put the pieces together to reassemble the original integral. So the integral from 0 to pi over 2 of ln 2 cos x dx is I1 plus I2. And previously we found that I1 is I pi squared over 8. And we just found out what I2 is. It's this sum right here. And I'm just going to factor out the I. And I'll carry this result to the top of the next slide. Okay, here we go. Now, I want you to notice something. The integral on the left is purely real. The expression on the right is purely imaginary. And yet these two guys are equal. There's only one number that is both purely real and purely imaginary. Do you know what it is? Yep, you're right. It's 0. That completes the integration, but we're not done milking information out of this thing. This expression in the parentheses is equal to 0. This tells us that the sum from 1 to infinity of 1 over 2k minus 1 squared equals pi squared over 8. So we didn't just find the value of a tough integral. We also found the sum of a series, which is very cool. But wait, there's more. Consider this sum here. It's the sum of the reciprocals of the squares of the natural numbers. I don't yet know what this p-series sums to, but I know that it converges absolutely to some real number, and I've called that real number s. So here I've rearranged the sum a bit. In the first set of parentheses, I've got the sum of the reciprocals of the squares of the odd naturals, and in the second set of parentheses, I've got the sum of the reciprocals of the squares of the evens. And I can write these two in summation notation like this. Now, we already know the value of the first sum. It's pi squared over 8. In the second sum, I've squared this 2 in the denominator to get 4, and I brought the 1/4 outside the sum. And notice that this sum here, sitting next to the 1/4, is exactly the same as the original sum, s. So I'll replace that sum with s right here. And this equation is easy to solve for s. You get s equals pi squared over 6. So we've squeezed out of this integral yet another sum of an infinite series. This baby's just full of surprises. This sum right here is the famous Basel problem, and it was solved by Euler in 1735. He didn't sum the series like I did, but he was the first to sum it. The problem is named after Euler's hometown of Basel, which is in Switzerland. And we can even get one more sum out of this. Right here, we have the sum of the reciprocals of the squares of the naturals. And right here, we have the sum of the reciprocals of the squares of the odd naturals. If you take these guys away from these guys, what do you have? You have the sum of the squares of the reciprocals of the even naturals. And so here you go. These are the reciprocals of the squares of the even naturals, and I'll just find that sum by subtraction. Pi squared over 6 minus pi squared over 8 is pi squared over 24. So the integral that we tackled in this video is a very rich one indeed. It gave us the sums of 3 infinite series. Summation of series is just as interesting to me as integration techniques, and one of these days I'll start a playlist full of videos on that subject. Thanks for tuning in to Weapons of Math Instruction. I hope you enjoyed this video, and I'll post Power Series Part 2 tomorrow. Bye-bye. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.